So this should be our last video on trig equations, and I'm going to do a couple more examples. This exercise is find all exact solutions in the interval from 0 to 2 pi for this equation sine 2x plus cosine x equals 0. Now, what's new here? Well, if you watch the previous video, you might be wondering, oh, there's that sine 2x. When you have an expression inside the trig function that's more than just x, more than just theta, something complicated, that complicates the situation, and that's true. But sometimes there's a way to rewrite the equation without that complication, without the 2x inside the sign. There are some situations where we can apply an identity to be able to simplify the solving of the equation. Also, another complication here I just want to mention is we have a sine and a cosine in the same problem. That's a bit of an issue because, you know, which one of those two do we isolate is what I'd be thinking right now. So here's what we can do. And so this is just the magic of trig identities being applied. So I whipped out my trig identity sheet here, and recall that we have this double angle identity for sine. Sine of 2 theta is 2 sine theta cosine theta. You know, what might make me think of this? Well, when I see that sine 2x, so we're going to apply the double angle identity. Maybe I'll write it up above here. Sine 2 theta is 2 sine theta cosine theta. So you don't have to have it memorized, but you need to be ready to apply it in certain situations, like right here, where we can rewrite this sine 2x in this equation as 2 times sine x times cosine x plus cosine x equals 0. And so we got to think about whether that's a good idea or not. I mean, the good side of it is we no longer have complicated expressions or things more complicated than just x inside our trig functions, right? We have sine x, cosine x, cosine x. You might think of this as a big mess, 2 times sine x times cosine x, and it is. So is it really a good idea to have that here? And I guess that the only way I see that it's a good idea is I realize that I can now factor the left-hand side of this equation. I can factor out a common factor of cosine x times 2 sine x plus 1 in parentheses equals 0. And now things are looking really, really good, because I can apply the 0 property and say cosine x equals 0, or 2 sine x plus 1 equals 0. And now this is split into 2 separate equations, and each one involves just one of the 2 trig functions. So we're looking 0 to 2 pi. 0 to 2 pi, where is cosine x equal to 0? That's going to be when x is equal to pi over 2 or 3 pi over 2. And on the right, if I isolate sine x, I have sine x equals negative a half. So now I want to think about sine x being negative a half in the interval 0 to 2 pi. So I'm going to have terminal sides below the x-axis. And now I know sine of pi over 6, or 30 degrees, is a half. So this is going to be, I could say negative 30 degrees or negative pi over 6, but we need to get angles between 0 and 2 pi. So I'm going to take 2 pi minus pi over 6 is going to be 11 pi over 6. So one of my solutions is 11 pi over 6. And now I need the other angle between 0 and 2 pi, so there's 11 pi over 6 is right here, that has that same y coordinate, right? And so that's going to be pi plus pi over 6, or that's right, pi plus pi over 6 is going to be 7 pi over 6. So this terminal side corresponds to 7 pi over 6. And I think there's nothing else that's fancy to this problem. There are 4 solutions, 2 from each of these equations things split up to it. The only tricky part is our little bit of unit circle calculation here. So let me just write x equals pi over 2, 3 pi over 2, 11 pi over 6, or 7 pi over 6. There are my 4 solutions to that equation. Okay. All right, one more example. And I'm going to move the sheet up here a bit so we can focus on this. Now, I wanted to do at least one example where we had to use a calculator, because it's a little bit artificial always having all our angles turn out to be 30 degrees or 60 degrees or 45 degrees or whatever. And so just here's one where we're going to have to use a calculator, but so let's see just exactly how that would work out. We're solving, this also involves tangent. Our first example with tangent, 2 tangent squared equals 5 minus 3 tan x. I guess because I see that tangent squared, it makes me think there's a quadratic situation here. It makes me think about factoring. So I'm going to get all the terms on one side. I can write this as 2 tangent squared x plus 3 tangent x minus 5 equals 0. And that is a quadratic in tangent. It could possibly be factored. If it helps, you can think of it as 2a squared plus 3a minus 5 equals 0. If you can solve that quadratic, you can solve this trig equation. Let's see, 2a, I'm going to use trial and error factoring here, 2a and a, 5 and 1, I think plus 5 minus 1 is going to give me plus 5a minus 2a, gives me the plus 3a in the middle. So what does this mean about tangent? It means I have 2 tan x plus 5 times tan x minus 1 equals 0. And so we're going to split into 2 equations. 2 tan x plus 5 equals 0, or tan x minus 1 equals 0. Now I'm going to isolate the tangent in each case. So tan x equals negative 5 halves when I isolate tangent, or tan x equals 1. And again, you can use a calculator to help you with this, but I hope we know now we've gotten used to the fact that one value of tangent, where a tangent's equal to 1, is at pi over 4, right? Because sine and cosine are both square root of 2 over 2. When we divide square root of 2 over 2 over itself, we get 1. And if I think on terms of the unit circle, so pi over 4 is here. If I want to think about any place else on the unit circle where tangent will come out to be 1, it's got to be the first or third quadrant, because in the second and fourth tangent's negative. I think you can see just totally symmetric straight down this line. It's like pi plus pi over 4, or 5 pi over 4 will be the other value between 0 and 2 pi. Pi over 4. and 5 pi over 4 are the two solutions we get from tan x equals 1. But now, what the heck do we get from tan x equals negative 5 halves? That's tan x equals negative 2.5 if you write it as a decimal. That's not a value. We know that's not a value I have off the top of my head, but I can use a calculator gives us x equals, what we can plug in is tan inverse of negative 2.5. So I'm going to use my calculator to get tan inverse of negative 2.5, and let's do it. 2.5 negative, then I got to hit a shift key. Oh, and then I guess the question is, are we in degrees or radians? I guess I better be in radian mode, and I wasn't, so I got to do it again. Why radian mode? Because the directions refer to 0 to 2 pi. We've already found some answers in radians. 2.5, change to negative. I'm in radian mode, inverse tangent. I'm getting that x is about negative 1.19. I'm going to write RAD for radians. Okay, that was harrowing enough, but now here's a bit of an issue. That negative 1.19, this is not in the interval from 0 to 2 pi, because it's negative for one thing. So how do we find, that's not the solution we want. The calculator is not giving us the solution we need between 0 and 2 pi. What we can do is use the period of tangent, which is pi, okay? So another solution is going to be negative 1.19 plus pi. And what is that? Negative 1.19 plus pi. Plus pi equals, I'm getting about 1.95 radians. Still another is negative 1.19 plus 2 pi. Let's see what that is. 1.19. Make it negative plus 2 times pi. I'm getting 5.09 radians. Now 2 pi, remember 2 pi is about 2 times 3.14, so 6.28. So these are both solutions that are between 0 and 2 pi. And I think if I add another pi on, I'm going to be too big. So my final answer here are our solutions to this equation between 0 and 2 pi are pi over 4, 5 pi over 4, which we got from the part we were able to do by hand in our heads, and 1.95 and 5.09. These are all radian measures. These were the two solutions. We got help from our calculator, but the actual calculator value we couldn't use because it was not in the interval from 0 to 2 pi. And we're done. But now what I want to do is, I know this was sort of a crazy problem. I want to look at a graph. Let's look at a graph of tangent and talk a little bit about what was going on in this problem. And let's see, I'm going to be able to fit enough onto this picture. Let's say negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi. Okay, I just want to be able to fit out to 2 pi. Tangent has vertical asymptotes at negative pi over 2, and pi over 2, and 3 pi over 2. And the tangent graph consists of these branches that repeat over and over again. 0 at 0, 0 at pi, 0 at 2 pi. Okay. And what we're looking at here, actually, I just want to talk about the calculator part of this problem. Like, what's this business about the negative 2.5 and the negative 1.19? Negative 2.5 is a value of tangent. Negative 2.5 is a y value on this graph. I'm just going to say, suppose it's like right here, negative 2.5. Now, if we move horizontally across, we hit all the points on this graph with y-coordinate negative 2.5. The inverse tangent function, tan inverse x, is defined by this piece of y equals tan x. So this is not the inverse function, this is tan x, but this piece of the inverse tangent, this piece of tangent defines the inverse tangent. So it's this point right here where the calculator is giving us negative 1.19. Okay, that's between 0 and negative pi over 2, negative 3/2. That's about negative 1.5 is a decimal right there, that negative pi over 2. So the interval from 0 to 2 pi, though, is from here to here, to the right of that y-axis. So that value we're getting from the calculator is negative. It's not in the interval from 0 to 2 pi. The two values I obtained by adding pi gave me an x value here. That's where my 1.95 is. And if I add another pi, I'm still less than 2 pi. This is where my 5.09 value is. So, I mean, maybe I'm getting a little carried away here, but I just think graphically it's nice to see the sense of where these strange numbers are coming from. They're input values, x values, that give us an output of negative 2.5 for tangent and happen to lie between 0 and 2 pi. So, I love that graph, but let's see, I'm going to just go back to the problem and leave the graph out of the picture just so you can see the worked out exercise. Maybe I'm going to slip it in there one more time just before we're through. To me, there's the picture. This has nothing to do with the pi over 4 or 5 pi over 4 values. This was just a picture of where those decimal radian values came from that I got from my calculator. All right, we're through.